Today we're going to shift gears a little bit and apply what we've learned about circular motion to heavenly motion. In other words, the motion of the planets and stars and things that exist up in the sky, up in the heavens. We'll do a little history lesson today. For those of you who like history, well, sorry, it's not going to be that long. For those of you who don't like history, good news, it's not going to be that much. But we're going to go back a couple thousand years to start off. Aristotle, who's more than 2,000 years, Ptolemy, who is a little bit after the birth of Christ. So we're talking about the time of Christ, give or take a little bit. The geocentric theory. What does that mean? Geo means earth. Centric means centered. The earth-centered theory. The earth is the center of the universe. The sun and everything else in the heavens revolve around the earth. The earth is the center of the universe. Now, that sounds silly to us. We know the earth is the center of our solar system, and the sun is the center of our solar system. And the earth revolves around the earth, and the earth revolves around the sun, and all the other planets revolve around the sun, and so on. We know this, right? But why do we know this? How do you know that the earth revolves around the sun? If you got up out of bed 2,000 years ago and looked up in the sky at sunrise, the sun would be rising over there in the east. And then a couple hours later, you'd notice the sun over there. And then a couple hours later, it would be over there. And so on and so on and so on until sunset, it's over there in the west. If you get out of bed a couple thousand years ago and you follow the path of the sun during the day, what's your natural conclusion? Sorry? It's going around. Yeah, the sun is orbiting around the earth, right? It comes up over there. We see the sun moving in the sky. We see it going over there. And then finally we see it going down over there. The earth is the center of the universe. The sun and everything else revolves around the earth. It makes perfect sense. I'm not smart enough to know the difference, except that somebody told me the difference. You're probably not smart enough to know the difference either, except that somebody told you the difference. So when we look at these guys, two historical figures thousands of years ago, it doesn't seem so bad that maybe they thought the earth was the center of the universe, because the rest of us would have thought that too. Okay, let's zoom forward a little while, like a long while, like 15 centuries or so, to Copernicus, 1543. How many people have heard of Copernicus? Yeah? Copernicus, the heliocentric theory. Helio means sun, the sun-centered theory. All of the planets, the Earth, Mars, Jupiter, Neptune, they all revolve around the sun. This is pretty controversial at the time. Like now, we all accept it, right? But 500 years ago, it's a pretty big deal, pretty controversial statement that the earth is not the center of the universe, that the earth rather revolves around the sun. Let's fast forward a little bit later, but now the time frame, the timeline kind of gets condensed. We're talking about 50 years later, the late 1500s, a guy named Tycho Brahe. He's an odd guy. Tycho Brahe is an odd guy. But he made some pretty good contributions to our knowledge of the heavens. He made naked eye observations. What does that mean, made naked eye observations? He looked up in the sky and saw things. In other words, he didn't use crazy telescopes. He just observed angles, distances, times, when this appeared, when that appeared. He didn't really do anything with them. He died really before he had a chance to do something with it. Odd guy. He's a mathematician. He got in a debate one time with this other guy about the correct answer to this math problem. Couldn't decide. What happens when you guys can't decide on what the correct answer to a math problem is? You have a duel. That's what he did with this person is, you know what, we can't settle on who's right about this math problem, so whoever wins this duel will be correct. So, as if somehow fighting with a sword and winning makes you correct about math. Anyways, he lost his nose. Literally, he lost his nose and had his metal prosthetic nose for the rest of his life. This odd metal prosthetic nose for the rest of his life, which, by the way, ended prematurely because one night he's at a dinner party. I mean, he's at a dinner party in the 16th century, so dinner parties aren't what they are now. He's sitting at the table. He's got to go to the bathroom. He's got to pee really, really bad, but thinks it would be rude to get up and go pee. So he sits there and he holds it, and he holds it, and he holds it. And then a couple weeks later, he ends up dying of an infection. So he died because he wouldn't go pee at a dinner party. So the moral of that story, I guess, is if you have trouble with a math problem, ask your math teacher. Don't duel it out with a sword. And if you got to go pee, like, just go. Just go, because we don't want you to die. Tycho Brahe, he made some contributions in the sense that he made observations, but we're going to think of him from here on out as the P guy. Tycho Brahe is the P guy. Now, Tycho Brahe's student, Johann Kepler, he's the guy that did something with that data that Tycho Brahe collected. He used that data to describe the motion of the planets. There's a bit of a typo here, by the way. He described how they move rather than why they move as they do. He came up with 3 laws, which we're going to describe in a few moments here, that did a really, really good job of describing the motion of the planets. This is where they go. This is how long it takes. This is everything about the motion of the planets, except for why do the planets do this? He didn't answer that. Now let's describe his 3 laws. First law is called the law of elliptical orbits. You guys know what an ellipse is? If you take a circle and stretch it out, that's an ellipse, right? Now, the law of elliptical orbits says that the path of a planet, including the Earth, is an ellipse around the sun. Not nearly as pronounced as the ellipse that I have drawn. It's much, much closer to being a circle that I have it drawn right here. But it's still an ellipse. I have it drawn much more pronounced than it really is, just so that you can see that it is in fact an ellipse as opposed to a circle. Now each ellipse has what we call 2 focal points. If we have an ellipse drawn like this, the focal point of that ellipse would be here and here. The sun will be at one of those 2 focal points. Now, that doesn't mean that the Earth revolves around like this in an ellipse, and then the sun decides, oh, I want to be here. And then the next day the sun decides, I want to be here. The sun is where it is. The sun doesn't change where it is. The sun doesn't decide to go based on where the ellipse is. Rather, it's the other way around. The sun is right here. Sun's right here. The ellipse could go like this, so that the sun was at one of the 2 focal points of the ellipse, or the ellipse of the Earth's path could go like this, so that the sun is at the other focal point. So the sun is fixed, it decides where to go, and is there. And then the elliptical path followed by the Earth and other planets around the sun bases itself upon where the sun is. But the sun still has to be at one of those 2 focal points. Does that make sense? So in words, we'd say the law of elliptical orbit says that the path of a planet around the sun is an elliptical path with the sun at one of, not both of, but one of the 2 focal points of that ellipse. Now the next one, that seemed a little bit confusing. The next one's going to seem even more confusing, at least the diagram is. So just wait to write this one down as well until I explain it. The second one's called the law of equal areas. And the law of equal areas says that essentially the area that's going to be swept out by a certain line, a certain imaginary line that joins the Earth or whatever planet and the sun, that area will be the same as another area during equal time intervals. So let's say the Earth is in position 1, and then, I don't know, a certain amount of time later on, maybe it's 2 days, maybe it's 2 weeks, whatever. A certain amount of time later, we call it T1, whatever time that is, the Earth is over here in position 2. Now fast forward 5 months, 6 months. The Earth is at position 3. Now the Earth going from position 3 to position 4, it'll take a certain amount of time. If those two time intervals are the same, in other words, if T1 equals T2, then the area in here, that's swept out by this imaginary line joining the Earth to the Sun will be the same as the area over here that's swept out by this line, this imaginary line joining the Earth to the Sun. Now, what does that mean? Like, so what? So those two areas are the same. As long as T1 is equal to T2, then A1 will be equal to A2, so what? Well, if these two times are the same, T1 and T2, the distances are clearly not the same. What implication does that have? Yeah?
If they're the same areas at the same time?
If they're the same, yeah, I mean, that's the law of equal areas, right? If it's the same amount of time, it's the same areas. But if these two times are the same, then these two distances are different, because they have to be in order to make the areas the same. Then what do we know about the speed of the Earth? As the Earth goes around the Sun, no, not at constant speed. It travels more distance right here in the same amount of time as it does over here. If T1 equals T2, then those two areas have to be the same, meaning this distance is bigger than this distance. So in other words, as the Earth's going around the Sun, it speeds up to cover the same distance in the same amount of time, or sorry, bigger distance in the same amount of time, and then it slows down over here. And then it speeds up, and then it slows down. And then it speeds up, and so on. Now, it's not nearly as pronounced in this diagram, just like it wasn't in the last diagram. I've got it drawn as a stretched ellipse, much more stretched than it should be, just so that you can see that it is, in fact, an ellipse, not a circle. But the effect is there. The speed of the Earth does change, just not nearly as dramatically as we have it shown in this picture, that's all. So if those two times are the same, then those two areas will be the same as well. And if those two areas are the same, then that means that the speed of the planet as it goes around the Sun must increase as it gets closer to the Sun. The third and final of Kepler's laws is called the law of periods. The law of periods says this: the square of the period of revolution of a planet, let's call it the Earth, divided by the radius cubed of the Earth's path around the Sun. Now, keep in mind, the radius changes, right? But we're talking about average radius of revolution here. T squared divided by r cubed for the Earth is equal to a constant that we call Kepler's constant for the Sun. Now, why is that a big deal? We're not going to solve any problems with this, so why is this a big deal? Why is it important? Well, because it would allow us to solve some pretty important problems. Let me move a little bit further, and then I'll explain to you what I mean by that. If we said t squared over r cubed for the Earth is equal to Kepler's constant for the Sun, then we could also say that t squared over r cubed for Jupiter is equal to Kepler's constant for Jupiter. Sorry, is equal to Kepler's constant for the Sun. In other words, The sun being our central body, the sun being our object that's being revolved around, has the same constant regardless of which planet we use data for. That's a big deal. Because if we know information about one planet, then that'll help us to get information about another planet. As long as we know stuff about the Earth going around the sun, then we can derive information about Jupiter going around the sun because the ratio of t squared to r cubed is the same. Okay?
Would that just be our sun or like other suns?
No. That's a good question. If we had, let's say, a random star. Let's say we had t squared over r cubed for planet 1 around random star. T squared divided by r cubed would give me a constant, Kepler's constant, for that random star. That would be a different Kepler's constant for the sun. Each central body or each object that gets revolved around has a different constant. But it doesn't matter what data you use for the orbiting object, you get the same value of Kepler's constant for that central body. Does that make sense? You could, yeah, the moon rotating around the Earth, yeah, absolutely. But then you would say Kepler's constant would be for the Earth, because Kepler's constant is always for the central body of the thing being revolved around. Does that make sense? So if we continue on this one here, we would say that, well, okay, planet 2 going around random star. T squared over r cubed for planet 2 going around a random star would also produce the same value of Kepler's constant, but different value than Kepler's constant for the sun. So each central body has a constant called Kepler's constant that's equal to the square of the period divided by the cube of the radius of revolution of any orbiting object around that star. Does that make sense? So I don't know anything about planet 2 around random star. It's newly discovered. But I know this and I know this. That allows me to get this. And now knowing this and knowing how long it takes to orbit around the sun or the random star, then I can calculate or I can determine the radius of revolution. So information from one planet allows me to find information about another planet. All right, we're missing the big question though. Why? Right, we said that this describes really nicely how the planets revolve around the Earth, but why?